Hey there. You know that incredible shimmering sound when a singer holds a long note? Or when you hear a cello? It's called vibrato. And we all know it when we hear it, right? But today, we're going to pull back the curtain and look at the wild science hiding inside what seems like just a single perfect note. All right, let's get into it. So let's start right at the beginning. What even is vibrato? We hear it constantly in all kinds of music, but what is actually physically happening? You might think the answer is pretty simple, but you're about to find out that our own ears and brains are playing some seriously amazing tricks on us. Now, most of us probably think we have a pretty good handle on this. We imagine a musician just, well, making the pitch of a note wobble up and down. A nice, smooth, controlled waver. And that's exactly it. That's the common idea, the thing that just makes intuitive sense to us. But what if I told you that what you're hearing, the thing that gives you that rich, emotional feeling, has almost nothing to do with the pitch at all? Okay, this is where it gets really interesting. This is the plot twist. Because when researchers started digging into the actual physics of these sound waves, they found something that was, frankly, a bit of a mystery. They realized that the vibrato we perceive is way, way more than just the pitch going up and down. This quote from a McGill University study just blows the whole thing wide open. Vibrato isn't one wobble, it's a mix of three different things all happening at once. First, you've got frequency modulation. That's the pitch wobble we all think about. But then there's amplitude modulation. That's a wobble in the volume. And finally, spectral envelope modulation, which is basically a wobble in the sound's texture or character. It's not just the note going up and down, it's also getting louder and softer, and its whole personality is changing, all in this one coordinated, shimmering dance. Let's really break that down. So on one side, you have frequency modulation. FM, classic pitch change, right? Just moving up and down the scale, but really fast. But then you have amplitude modulation, AM. This is about volume. And here's the trick. It's not the overall loudness changing. A single musical note is actually made of tons of little individual tones. AM vibrato is when the volume of each of those little pieces is pulsing up and down. It creates this shimmering effect all on its own. And that brings us to this absolutely mind-bending idea called amplitude modulation vibrato, or AMV. This is the core of the mystery. It is totally possible to hear vibrato in a sound that has zero change in pitch, none. The whole effect comes from that complex shimmering of all its little volume parts. So that kind of begs the question, right? If the pitch isn't changing, what is our brain hearing that makes us think it is? So to figure this out, scientists at McGill put on their detective hats. They decided to take one single cello note and completely deconstruct it to figure out the rules our brains are following to hear this pitchless vibrato. They needed to know what was essential and what was just extra. So the first step was to get the recipe. They took that cello note and broke it down into all its basic ingredients using this sinusoidal model. Every one of those vertical stripes you see is one of the individual sound waves, or partials, that make up the rich sound of the cello. They could see each one's frequency and its energy. It's like having the complete blueprint for one sound. Okay, so once they had that blueprint, they started building their own sounds. First, they made a perfect digital copy. Then, step 2, they took out the pitch wobble completely. Gone. Step 3, they started messing with those volume wobbles in very specific, controlled ways. And finally, they played these weird new sounds for a bunch of people and asked them two simple things. How realistic does this vibrato sound? And does it sound like it's coming from one single source, a quality they called unity? They were basically trying to figure out what our brains actually care about. Do all those little volume pulses need to be perfectly in sync? Do they have to sound like they could come from a real cello? And just how much do they need to pulse to create the effect in our heads? And the results were, well, they were pretty wild. They revealed some really surprising truths about how we hear the world, and they show that our brains are a lot more creative and a lot stranger than you might think. And here is the big reveal. It turns out our brains don't actually need a perfect, physically accurate sound to hear vibrato. Not even close. We're constantly filling in the blanks. Our minds are pattern-seeking machines, and when they detect a pattern, like a bunch of sound parts all wobbling at about the same rate, they just construct the perception of vibrato for us, even if the sound itself is totally possible. This quote from the study nails it. Plausible resonant structure. That's just a fancy academic way of saying a sound that could actually come from a real instrument in the real world. And what they found is that it's just not necessary. The sound can be physically impossible, but if the volumes of its parts wobble together, our brain goes, aha, I know what that is. That's vibrato. But they found this fascinating trade-off. The sounds that had the most complex and messy wobbles, the ones that were most like a real instrument, were the ones people rated as having the most realistic vibrato. But get this, listeners rated those exact same sounds as being less unified, meaning it sounded more like the sound was coming from a bunch of different places at once. So the thing that sounds the most real is also the thing that sounds the least like a single object. How weird is that? So, we've seen how our brains are literally building the idea of a perfect note in our heads, but that's only half the story, right? What about the actual source of the sound? The search for that perfect vibrato doesn't just happen between our ears, it starts with the very materials that make the music in the first place. Yeah, we're making a leap here, from the psychology of how we hear to the actual physics of an instrument. It turns out, to create that perfect sound for our brains to play with, instrument makers have been obsessed for centuries with the wood they use, right down to the cellular level. And this brings us to one of the wildest studies I've seen in a while. In 2014, researchers discovered you could make better violin wood by treating it with fungi. I'm not kidding. They took the traditional woods, Norway spruce and sycamore, and let specific fungi work on them. The fungi gently ate away at the wood, reducing its density. And the result? Wood with enhanced acoustic properties. Wood that could literally create a richer, more beautiful sound. So, let's put all this together. What does this all mean? We've seen that the sound we hear isn't just a passive recording of the world. It's an active construction, a partnership between an instrument and our own mind. And that's really the big idea here. That beautiful, shimmering quality of a perfect note isn't just a sound wave hitting your ear. It is a delicate dance. On one side, you have the physics, the microscopic structure of wood, maybe even helped along by some friendly fungi. And on the other side, you have the incredible predictive power of your own mind, taking all those complex signals and building the feeling, the emotion of a perfect vibrato. Which leaves us with one last question to chew on. The next time you're listening to music and you hear that soaring vocal line or that rich cello note, think about that incredible dance between physics and perception. Does knowing the secret science behind it all change how you hear the music?